Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating work in AI. Specifically, we're looking at a paper titled Prior Does Matter: Visual Navigation via Denoising Diffusion Bridge Models, published just recently on April 14th, 2025. So, the core idea here is about improving how robots learn to navigate visually using diffusion models. The researchers point out that starting action generation from random noise like typical diffusion models do isn't very efficient for navigation. Instead, they propose NaviBridger, which uses what's called a diffusion bridge model to start from a more informative prior action, essentially giving the model a better starting point. Okay, and speaking of the practical side of things, the researchers have actually made their work quite accessible. What we're looking at here is a snapshot of their GitHub repository for NaviBridger. So, you can see the code structure, the README file explaining things. It basically gives you everything you need, like the training scripts, data preparation steps, and even how to run inference, maybe on a Jetson device like they used in their real-world tests. It's great to see this level of detail shared. Alright, and this figure 1, really helps visualize the core difference they're talking about. So, on the top row, you see the standard diffusion approach. It starts with pure noise, basically random guesses for the path, shown as those messy yellow lines overlaid on the image. Then, through the denoising process, it tries to clean that up and eventually arrive at a sensible target action or path. But look at the bottom row, that's NaviBridger. It doesn't start from random noise, it starts from a prior, a more informed guess about the path. You can see the initial yellow lines are already much more structured. Then, the bridge denoising refines that initial guess to get to the final target action. It visually shows how starting with a better guess, the prior, helps guide the process more effectively towards the desired path. Okay, so building on that visual idea, Figure 2 gives us a more detailed look under the hood at the NaviBridger architecture itself. You can see it takes the robot's current observations and the goal image as input, uses a transformer encoder to extract features, and then, crucially, it feeds this into the prior generation module. This is where those different starting points we talked about, like the Gaussian noise, the rule-based prior, or the learning-based prior, are actually generated as a source action. Then, that source action goes into the diffusion bridge module, which does the refining process we saw conceptually, bridging the gap to the final target action. Alright, so that brings us to Table 1, which gives us the hard numbers from their simulation experiments. It compares NaviBridger, using those different priors we just saw, against existing methods like Nomad and Vint. They look at things like how successful the robot is, how many times it collides, and the path length across different indoor and outdoor scenarios. The big takeaway here is that NaviBridger with the learning-based prior consistently comes out on top, especially in the trickier adaptation tasks. For instance, indoors, it hits an 88% success rate compared to only 32% for Nomad. It really shows that starting with a better learned guess makes a big difference. Okay, and building on those simulation results, Figure 4 gives us a really nice visual comparison of the path generation process itself, both in simulation and in the real world. So you can see across the columns, these are the different denoising steps, from step 0 up to step 10. The top row is Nomad, starting from noise, and you see how chaotic those initial yellow path predictions are. It takes quite a few steps for it to settle down. But then look at the middle and bottom rows, which show NaviBridger with the rule-based and the learning-based priors. Especially with the learning-based prior, the path starts much more reasonably at step 0, and it quickly converges to a smooth, stable trajectory in just a couple of steps. It really drives home the point visually, that starting with a good prior helps generate better paths much faster. Going further, Figure 5 quantifies that speed advantage we saw visually. So it plots the success rate. That's the blue lines, and the inference time, the orange lines, against the number of denoising steps. We can see that NaviBridger with the learning-based prior, the solid blue line with squares, achieves a high success rate with fewer steps compared to the standard diffusion model, the dashed blue line. Of course, more steps mean more processing time, but this shows NaviBridger, especially the learning-based one, finds a really good balance, getting high success without needing excessive steps. Okay, and Table 3 gives us another really important piece of the puzzle. It isolates the effect of the prior action, the source, compared to the final target action after the diffusion bridge has refined it, specifically in that challenging indoor adaptation task we saw earlier. So, if you look at the source rows, using just the initial guess from the prior, the success rates are quite low. Even the learning-based prior only gets 20% success on its own. But after the diffusion bridge does its thing, look at the target rows. The success rates jump dramatically, especially for the learning-based prior, reaching 88% with far fewer collisions. It really highlights how crucial that bridge refinement step is, taking those priors and turning them into effective actions. Okay, and digging a bit deeper into the model's accuracy, Table 2 gives us a comparison of the mean square error, basically how close the predicted action is to the expert action. It compares NaviBridger, specifically the version using the Gaussian prior, against the standard Nomad model, across different datasets and numbers of denoising steps, K. Well, the main thing to notice is that NaviBridger generally achieves a lower error, especially when using fewer steps, like K equals 1. You can see this reflected in the average rank, where the Gaussian prior method consistently scores better, meaning lower error, than Nomad. This suggests the bridge model is more stable and accurate, even when we try to speed things up by reducing the denoising steps. Alright, so pulling all these results together, the accuracy we just saw, plus the success rates and efficiency gains, really highlights the power of this NaviBridger approach. It shows how integrating prior knowledge effectively within a diffusion bridge model can lead to significantly better visual navigation, making robots potentially faster and more reliable in tricky environments. It's promising work for applying these kinds of generative models to robotics. Well, that's our roundup for today. Thanks for tuning in. I'm Alex, your host for the AI Research Roundup.